Okay, everybody to the last afternoon session today. The next talk will be by Romina Arroyo and from Cordoba, and she will tell us something about almost abelian complex nilmanifolds.
Okay, thank you very much for the presentation. First of all, I would like to thank the organizers for this kind invitation and for giving me the opportunity to be here and to speak about my work. So thank you very much. And of course, this is my first time in Sofia, so I am excited too. So thank you for that. So today I'm going to speak about almost abelian complex nilmanifolds, and so in my abstract. So I promised to speak about this project with these people. But when I started to prepare the talk, I realized that this work is based basically on this other work, which is a work doing by a group of women. So at some point, I am going to show you at the end of the talk some of the results, but I also would like to focus on this other work because it was I would like the idea to think that you are going to take these names of this group of women and you will have in mind more women doing mathematics. Yeah. And in these topics related with the topic of the conference. So I'm going to start with the motivation, which is a differential geometry motivation, but faster I'm going to move to Lie algebras, and maybe in 15 minutes I am going to be working with linear algebra, which is more easy for everybody. So Maria Laura Barberis, Jamile Godoy, so they work in Cordoba in my same university. Veronica Diaz is from Argentina too. She's working in University of Mar del Plata. And Isabel Hernandez is from Mexico. She works in Mérida, in CIMAC. And Adriana Andrada is also from Cordoba, Argentina. And Sonke and Konstantin, they work in the University of Mar. Okay, so I want to start with this article, which is also published in Journal of Geometric Analysis, and this one is already accepted in Revista Matemática Complutense. Okay, so I am going to start with the definition of a complex manifold. So here I would like to draw a picture. So basically, maybe you know what is the definition of a double manifold. So the definition of a complex manifold is basically analogous, but so you are going to have a topological space, and for any point you have opens and maps going to, in general, for differential manifolds, going to Rm. So these maps are homeomorphisms between neighborhoods of P and opens to Rn. And if you have another open overlapping, so you have another homomorphism with another open to Rm. And in the setting of differential manifolds, so you know that these maps, which are called transition maps, are so we ask to be this transition to be differential. So at some point, this we ask to be differential. So what is the difference with complex manifolds? So now we have again a topological space with this setting, but the difference is that so here we are going to CM and this transitions map. So this composition is holomorphic. So at some point, if you have this object, this mathematical object, so if you have a complex manifold, you will have doing this identification, so you will have a differentiable manifold but of even dimension. So any complex manifold is a real differentiable manifold of the double of the dimension, the original. But if you start with a complex manifold, so then you get this differentiable manifold, but the first natural question is, if you have a differentiable manifold of even dimension, do you have a complex manifold? And the answer in general is no. Is no, you need a little bit more, and the one definition which is equivalent is this one. So the object that you need is this endomorphism. So this one tensor on the tangent mapping of M, satisfying that the square is minus identity. So you will need something like the imaginary numbers, and you also need that this tensor, which is called Nash-Hines tensor, vanishes. So first, second natural question is, so do we know examples of complex manifolds? And yeah, we know plenty of them. If you use this definition, you will believe me that these are examples well known. So we have in every dimension examples of complex manifolds, but there are more of them. So my idea is try to show you or try to convince you that we will construct or we will have examples of complex manifolds which do not come from CM, basically. In order to do that, so we'll be working with Lie groups and Lie algebras. Okay, so basically, so this part of the talk is similar to the second talk of yesterday, and my interest is try to find more examples of complex manifolds. Try to understand complex geometry in general, and Lie groups is a rich space of manifolds where we can look for these examples. So in particular, of course, I like to work with algebra, and that's the idea to use also these Lie groups. So we'll be using the correspondence between Lie groups and Lie algebras, and the correspondence between tensor, left invariant tensors, and some objects on the Lie algebra. So the picture will be, so we are going to start with a simply connected Lie group. So if you have a simply connected Lie group, so you can define the Lie algebra, that is so well known. And if you have, so in general, if you have a complex structure, so you can focus on the identity in general. If you focus in the identity, so the Lie algebra, since we are working with complex manifolds, so we are going to have a real Lie algebra of even dimension, and because of the definition of the complex structure, so we are going to have these two conditions on this endomorphism at the Lie algebra level. So the first one is the identity, and the second one corresponds to the Nash-Hines tensor, vanishing. But the good thing is that if you have this information, a Lie algebra with this package, so these two conditions, so then you can consider the simply connected Lie group associated to this Lie algebra, and you can use left translations on the Lie group and construct a left invariant complex structure. So at some point, if you want to say things about Lie groups with complex structure, left invariant complex structure, so you can work at the Lie algebra level, and that is the idea of this talk. So in general, I am not going to put any more this sub E. The notation will be JP. And what is the definition of a complex nilmanifold? That is two words that appear in the title of the talk. So basically, it's a quotient, a compact quotient of a real nilpotent Lie group G by a discrete subgroup equipped with a complex structure coming from a left invariant complex structure on G. So basically, we'll be working with Lie algebras, which admit these quotients. So I am telling you things in advance. So we'll be working with Lie algebras, which Lie groups admits these discrete subgroups that makes a compact quotient. So the next question is, okay, so now we have a Lie algebra. We have this condition. What we know about complex structures on nilpotent Lie algebras in general. So what is known? And here I would like to show you what happened in low dimensions, and to say some things about this. Of course, is not. So of course, these are not all the results. So there are more results, but it's something that you have the feeling of what happened on Lie algebras. So the first dimension, which is important, is dimension 2. And in dimension 2, there exists one Lie algebra up to isomorphism, which is the abelian Lie algebra. And if you have the abelian Lie algebra, basically the brackets are 0. So this condition always is satisfied. So the only thing that you need is in a vector space an endomorphism J satisfying that square is minus the identity, and that is easy to construct. So the two-dimensional nilpotent Lie algebra admits a complex structure at the Lie algebra level. And of course, if you have any other abelian Lie algebra, it will be the same. So if you can construct an endomorphism satisfies that the square is minus identity, you will have a complex structure. So what happened in dimension 4? Well, in dimension 4, up to isomorphism, there are 3 nilpotent Lie algebras. One is the abelian one, so that admits a complex structure, and then there are 2 more. One of them is this one is the sum of R with H3. H3 is the Heisenberg Lie algebra that also was mentioned in the second talk, and it's pretty easy to construct a complex structure here, because basically, so the bracket here is, so we have X, Y equal to Z, and then we have another element, I don't know, we may call W, generating this as a vector space. And the bracket, the only non-zero bracket is this one. And if you consider the endomorphism extending X to Y and J Z to W, and then to make that the square is minus the identity, so this, and you use that you need that this endomorphism to be linear, so you extend linearly, so you will have an endomorphism satisfy this thing, and then you can check that this is also satisfied. And the other one, the other Lie algebra of dimension 4 is a filiform nilpotent Lie algebra. And it is well known that if you have a filiform Lie algebra of any dimension, will not admit a complex structure. This was proved by Gosser and them in 2002. So here you can see that in any dimension, so you have nilpotent algebras which admit complex structure and nilpotent algebras which do not admit. So what is the picture in dimension 6? So there are 34 nilpotent algebras up to isomorphism, and only 18 admit the complex structure. So at some point you can try to find numbers in these two dimensions. This was proved by Salomon, I'm sorry. But the thing is that it's difficult to say if an nilpotent algebra admits or not a complex structure in general. So, and this is the picture that I would like you have in your mind and you take to your home. That from dimension A, there are infinity many nilpotent algebras. So we have curves of nilpotent algebras, which are not isomorphic 2 by 2. And so in dimension A, still there are classification results about nilpotent algebras. From dimension 10, there is no more classification. And if you fix one of these infinity many nilpotent algebras, and you ask the question about if you have this object, it's difficult to answer the question, even if you use the computer. That's difficult. So from dimension A is considered like a wide problem. So try to understand or to say things about this. In general, it's impossible. So at some point you have to focus on a class of the algebra. And we are going to focus on this class of the algebras that in principle these are not nilpotent, but then we are going to restrict in the nilpotent case. So what is the definition of an almost abelian Lie algebra? So basically, an almost abelian Lie algebra is a Lie algebra which has a big abelian ideal. So an abelian ideal of codimension 1. So what happens when you have that? So if you consider the abelian ideal, and then if you take one element outside of that ideal, so you will have one element, I don't know, I call it E naught, acting on the elements on the ideal. And if you fix a basis on the abelian ideal, so I am calling Rn, so you will have the action of this element on these other elements, and then since this is abelian, so here, the bracket here is going to be 0, so all the information of these Lie algebras are determined by an endomorphism or a matrix A. So if you have a matrix A, you can construct an almost abelian Lie algebra, and if you have an almost abelian Lie algebra, you have a matrix which determine the Lie algebra. Observe that this Lie algebra, so this is in general, there is no even dimension here, but if the Lie algebra has dimension m plus 1, the ideal has dimension m, and this matrix is restricted to the ideal, so this is an m by m matrix, so the dimension is one less, the size is one less. So we're going to call GA this Lie algebra. And in general, these Lie algebras are not nilpotent, so these Lie algebras are solvable. But if we restrict to the matrices which are nilpotent, so we have that the Lie algebra is nilpotent, and this is if and only if. So in order to work with a class of nilpotent Lie algebras, we are going to consider this GA Lie algebra with a nilpotent, and as you can see, you have infinity many Lie algebras, because in every dimension you have Lie algebras. Of course, in any dimension you have a finite Lie algebras of this type, but you have it in every dimension. Okay. So what is the notation that I am gonna use? So the idea is that we want to say when this almost nilpotent, almost abelian algebras admits a complex structure. And the way to say this is working with, this is the linear algebra part. So we are going to work with the Jordan normal form of the matrix. So basically, this is the notation. I am going to denote a Jordan block by Jn. And if the this big zero is going to be a matrix S by S, which is 0. And if I am going to denote these matrices, these block diagonal matrices, with this notation. So in general, if you have an important matrix of size n times n, which is non-zero, so we know, because of the Jordan normal form, we know that A is conjugate to a matrix like this. And here I didn't write this notation, but basically here I am telling that the blocks of size M1 appears Q1 times. So this is going to be a big, I'm sorry, a big M1, J M1, J M1, this Q1 times, and then M2, 2 to 2, these are zeros, and at the end, JMK, and then a big zero. I am ordering the blocks like this. I am asking different to 0 in order to have these blocks. If not, you only have the 0 block. So what we could prove with this group of women last year. So first of all, we used a result of Jorge Laurel and Edwin Rodriguez Valencia, which says that if you have an almost abelian Lie algebra, the almost abelian Lie algebra, nilpotent, will admit a complex structure if and only if A is conjugate to a matrix like this, with B satisfying some condition. This 0 is this is like a small 0. So here I have a vector which is 0. Here B, and this is B. And Laurel and Rodriguez Valencia said that admits a complex structure if and only if B satisfies something. So the first thing that we prove is that in order to admit a complex structure, the Jordan form of this B has to be like this. So all the Jordan blocks has to appear even times. So here QR are evens, and the block, this 0 block has to be even too. So the size of this matrix has to be odd, because the big Lie algebra is dimension even. So then the matrix is one less, so it's odd, and this is odd. So the size is even. I'm sorry, and there I have one. So all the Jordan normal blocks has to appear even times, and this has to be even too. So then, when that happens, so the next natural question, okay, so I know the Jordan form of this matrix. So I know the form that what thing satisfies the Jordan form of this matrix. So what are all the possibilities of the Jordan form of this other matrix? Well, there are different Jordan normal forms for A. for instance, if this B is in the image of this other capital B, so then the matrix will be conjugate to this one. So basically, you can put a 0 vector there. But if B is in the image of this capital B, so we have like two options. One of them is that the Jordan normal form of A is basically the same than B, but one of these blocks disappears. So here, the block J and B appears one less time than there, but appear one more. Or the Jordan normal form is the same and appear one J2. These are the three forms. And in order to show you why this happened, I am gonna, so here I put an example basically. So this is an example of the first case. So basically this vector lies in the image of here. So we can put a 0, is conjugate to put a 0 here. So then this matrix is conjugate to, if you put a 0, so you can see that. So here you have a J3 there, and then you have 2 zeros, so it's J3 plus the O2. If you have something which doesn't lie in the image of this B, so you can have something there, or you can have something there. So these are the easiest examples. And if you have something there, if you look at this matrix, so there, your J3 now is a J4, and you have a 0. And here, if you look at these 4 points, so the J2 appears. So basically, these are all the examples. And well, we have a proof of this. But here I am focusing on the Jordan normal form of B, not in the Jordan formal norm of A. So in this theorem, so we write the version focusing on A. So if we start with an enormous abelian algebra with the Jordan normal form of A, so like this, so the size of M is odd, so then GA will admit a complex structure if and only if one of the following conditions is satisfied. One and only one. So the first one is in corresponding with the first case. This one, which nk equal to 2 appears, is in corresponding with the last item in the previous slide. And this one is when appears a new Jordan normal block. But basically, so it's easy. If I give you a enormous abelian algebra, or you give me an enormous abelian algebra, I take the A, I compute the Jordan normal form, and once I have the Jordan normal form, so I can check if one of these conditions is satisfied. And then I can tell you if admits or not a complex structure. And of course, in the proof of the theorem, you can see what is the complex structure. So here you can see that there are many examples of nilpotent algebras admitting a complex structure. Well, all this part of the talk was thinking about in the first article, but focusing on speaking in the second part, which is the second article. And so here I would like to do some remarks. So I was speaking about nilpotent algebras, but in this article with this group of women, we dropped the nilpotency assumption on A. So at some point, so we we can say when an almost abelian admits or not a complex structure. We drop in the potency. And we also have an analogous result about which are the almost abelian algebras admitting symplectic structures. So we have a similar theorem written in terms of the Jordan normal form of A. But I focus on the nilpotent case because I am going to speak about the other work. And so one other natural question is, okay, so now we have the picture of which nilpotent almost abelian algebras admits a complex structure. So the next question is how many complex structures they admit. So it is just one or there are more. So it's a unique that the complex structure that we show in the proof that I didn't show the proof, but in the proof you can see a complex structure. And so this is the definition of when two complex structures are equivalent. So are equivalent is basically there exists a map, an isomorphism, an isomorphism of the Lie algebra satisfying this condition. And the first result that we proved with people working in Marburg is that if one of these Lie algebras admits a complex structure, all of them are equivalent. So at some point up to equivalency, there are just one complex structure, and not anymore. Just one. The one that you can see in the proof of the art. And here I am basically introducing this definition. Is just a definition. I am going to use this then in order to say something about the cohomology. But basically, if you have an nilpotent Lie algebra and a complex structure on the Lie algebra, so this Cordero, Fernandez Gray, and Ugarte, they introduced this definition about the complex structure. So they say that the complex structure is nilpotent if the complex structure satisfies this condition. And basically, if you can see, the way to write the definition is to introducing these ideas which are defined inductively. So the first one is 0, and the second one, for instance, if you can see, the second one is A1, J is all the elements on G satisfying that the bracket with G is equal to 0, and J, these elements, the bracket with all the elements on G is equal to 0. So in this case, A1J is basically the intersection between the center and J the center. And then you can define inductively. At some point, if you get G with these ideals, the complex structure is called nilpotent. And so the second result that we could prove with people from Marburg is that our complex structures are nilpotent. And this is going to be important for people. Well, this is part of my promise. So now I'm going to try to explain some results about the cohomology. So first, we started to study the ramp cohomology. So here we have this exact sequence. So here A again is the abelian ideal of codimension 1. This H is basically the space generated by this enough. So the space is in the dimension 1. So here you have the action, and the action is given by this matrix A. And of course, you can extend the action of H to the lambda. And the first result that we could prove is the following. So here, this is the ramp cohomology, and it is well known that in the case of nilmanifolds, the RAM cohomology can be computed with less invariant forms. So it's the same as the cohomology, the RAM cohomology at the algebra level. And we could prove that in order to compute this thing, so we have to compute this other thing. So at some point, the other powers of H that do not appear. And here is important this condition of nilpotency on J, because here I would like to speak about the Dolbeault cohomology. So here, if you have a complex structure, so you have del and del bar maps, and in general, you can consider the cohomology with del bar, and it is also satisfying that if you consider the left invariant forms, so there is an inclusion between this object, which is at the algebra level, in the Dolbeault cohomology of the nilmanifold, well, of the manifold. Yeah, but this is in the nilmanifold. See, this inclusion is always satisfied. The conjecture in general is that if this inclusion is an isomorphism or not. And there are how do you say one? Supporting results telling that the conjecture could be true. These are all the cases in which it's known that the conjecture is true. In particular, if you have a complex structure which is nilpotent, so this inclusion is an isomorphism. So at some point, this is telling us that if you want to compute the Dolbeault cohomology, so you can use less invariant forms. So you can compute at the algebra level. So then, so again, if you consider this exact sequence like this, and you want to compute the Dolbeault cohomology, this first isomorphism is the isomorphism that I spoke in the previous slide, and then we could prove that in order to compute this thing, so we have to do these computations. Again, the powers H are 0 from 2 or. And with these results, so we could prove also that in order to compute the complex Dolbeault cohomology, so you have to compute this sum. So in particular, the Betti numbers are equal to the sum of the Hodge numbers, which are the dimension of this. So this is well known in the Keller case, but in general, it is not. So in our opinion, it's a nice result. And that's all. Thank you.
Very much for a very interesting talk and question.
So your manifolds are only complex.
Yes, here.
Yes, you know that they are okay.
No. These are all of them are not Keller.
You know this.
Yeah, because when you so you are Keller if and only if you are a torus. So at some point the Lie group has to be abelian. So all of this almost abelian which has one Jordan Foreman block different to 0 is not Keller. Yeah, there's plenty of examples of non-Keller geometry. Thank you for that question.
Other questions? If not, then you again. And we meet in 10 minutes.